One of the greatest ideas to come out of Einstein's general theory of relativity was the recognition that space and time are combined into a single entity called spacetime. Not only that, but the presence of matter and energy curves the very fabric of spacetime, and that curved spacetime in turn dictates how matter itself moves. In order to visualize this concept, we're going to use a 2D depiction of the fabric of spacetime and see how much this fabric gets distorted by objects of different mass. A lighter object, like a moon for example, may not distort spacetime that much, whereas a heavier object, like a star, would create a relatively severe distortion of the fabric. Thus, the more massive the object, the more the fabric of spacetime is bent around it, and the more likely nearby objects are to fall into that curvature, creating the phenomenon we know as gravity. What about massive objects that are moving, or more particularly, accelerating? Einstein's theory tells us if spacetime can bend, it can also ripple, creating gravitational waves that propagate throughout the universe from their source. If you can imagine throwing stones into a pond, you can visualize the ripple pattern these waves create. The heavier the stone you throw, or the harder you throw it, the farther out the ripple pattern goes before it finally dies out. But every stone, no matter how light, still disturbs the water's surface somewhat. Similarly, everything in the universe that has mass and acceleration is generating gravitational waves. Not just celestial bodies, but cars, planes, trains, and even our own bodies. However, the gravitational waves that you and I produce are so small scale that there currently exists no instrument sensitive enough to detect them. Only the universe's most catastrophic events have ever produced gravitational waves detectable by scientists on Earth. So far, these have all fallen under a category called compact binary in-spiral gravitational waves. These are produced by orbiting pairs of massive, dense objects like white dwarf stars, black holes, and neutron stars. There are three types of compact binary systems: binary neutron star, binary black hole, and neutron star black hole binary. Each binary system creates its own unique pattern of gravitational waves, but the way the waves are created is always the same. Over millions of years, the compact objects orbit each other closer and closer, faster and faster, and finally ending in a terrific collision. The first gravitational waves ever detected were actually from a black hole collision, and scientists were able to convert its space-time distortion signals into an audible sound called a chirp. So if you ever wanted to hear the last words of two black holes, they sound like this.